Hi everyone, my name is Qiangyu. I'm from Huazhong University of Science and Technology. Our talk introduces a hotspot-relievable warm water cooling system for saving cooling energy of the emerging edge data centers. Recently, the emerging edge services, such as autonomous vehicles and augmented reality, require ultra-low latency, high bandwidth, real-time access, and so on. Edge data centers are promising for satisfying strict requirements. Firstly, the edge data centers are usually located in proximity to end users. Secondly, the edge data centers are usually equipped with heterogeneous hardware for supporting diverse edge applications. Thirdly, considering the land scarcity of the urban and the deployment of various high-powered hardware, the edge data centers tend to have a high power density. The growing demand for edge data centers leads to a high power footprint. The global power footprint of IT equipment in edge data centers will increase tenfold in the next 6 years. Besides the IT equipment, there are other kinds of facilities in a data center, such as the power system like UPS and the cooling system. The empty equipment usually contributes over half of the total facility energy, and the cooling system dominates the rest. A useful metric of power usage effectiveness is usually used to indicate the energy efficiency of data centers. It's calculated by the total facility energy dividing the anti-equipment energy. Although the PoE of cloud data centers can reach near 1, the PoE of edge data centers is as high as around 2, showing the low energy efficiency of current edge data centers. We argue that it's urgent to improve the PoE of edge data centers, while reducing the cooling energy is the most effective way. However, the new requirements of edge data centers make existing cooling techniques inefficient and even impracticable. First of all, proximity to end users will disable free cooling, since this cooling technique requires free cooling sources like cold air and cold water that are inaccessible in the urban. Secondly, air cooling has a hard time dispersing heat from servers with a high power density. Thirdly, although water cooling is the most promising cooling technique, the heterogeneity makes the thermal imbalance more severe, and the conventional coarse grained water cooling system become exceedingly inefficient. In a conventional coarse grained water cooling system, all the servers and internal components share the same water temperature and flow rate. Each component is directly attached to a cold plate and disperses the heat to the internal cooling water. After absorbing heat from different hardware components, the water gathers together and then is cooled to some temperature by the chiller. For the safety of all hardware components, this temperature is usually set to be low enough so as to cool down some high utilization hardware components with a high temperature. However, since other low utilization hardware components are overcooled, this wastes a huge amount of cooling energy. Recently, warm water cooling has been proposed to save the cooling energy by reducing the use of the chiller. Since the water temperature can reach 40 to 45 degrees Celsius, that is higher than the ambient temperature, the water flowing in pipes and tanks can disperse the heat directly to the ambient environment. By leveraging this natural heat dissipation phenomena, less energy will be consumed by the chiller. However, although it's less likely to overcool any hardware component and save the cooling energy, some high utilization components, known as hotspots, can be overheated. This may degrade hardware performance, shorten hardware lifespan, and even lead to system breakdown. Typically, there are two kinds of hotspots in data centers, including the hardware-level hotspots and chip-level hotspots. Here, we present 3 examples, including hotspots among different components, among CPU cores in a CPU, and inside a CPU core. As we can see, the temperature variation can be over 20 degrees Celsius. What's worse, the hotspot issue can get worse in edge data centers, owing to the requirements of high density and heterogeneity, along with the skilled hardware utilization of edge workloads. Although there are several existing solutions to the hotspot issue in cloud data centers, they have important limitations in edge data centers. For the software-based solutions, it's usually necessary to consider the trade-off between the performance guarantee and hotspots relieving, since end users would place strict demands on performance. For example, some mission-critical edge applications would have no deferrable workloads. Recently, Zhang et al. Proposed a hardware-based solution to the hotspot issue for CPU. They integrate each CPU with a thermoelectric cooler to deal with hotspots. They also add a copper sheet and another cold plate to disperse heat when the TEC is turned off. However, this solution fails to meet the requirements of edge datacenters, including high density and heterogeneity. Firstly, although the required space for CPU is acceptable, it can take up large space for sizable components like GPU. Secondly, such modifications would fail to support heterogeneous hardware components, considering their various physical layouts. In addition, the above solutions are designed to relieve only hardware-level hotspots, and the chip-level hotspots are not well considered. Facing the strict requirements by edge datacenters, how can we relieve multiple level hotspots while saving the cooling energy? Our solution proposes a fine-grained warm water cooling system named CoolEdge to relieve multiple level hotspots with the least cooling energy. In a conventional coarse-grained water cooling system, all the hardware components share the same cooling water temperature and flow rate, and the heat are absorbed by the cooling water through copper-based cold plates. To eliminate hotspots among different components, we redesign cooling loops named inner loop and outer loop that customize the water temperature and flow rate for each hardware component by mixing certain amounts of hot water directly from the water tank and cold water from the chiller through a valve. To disperse hotspots inside a component, we integrate vapor chambers into cold plates that realize vapor fluid mini loop. The vapor chamber can not only lower the overall hardware temperature, but also reduce local hotspots by smoothing the temperature distribution. We also design a control system that collects real-time hardware information, decides the best cooling setting, and implements the setting by tuning the flow rate of each valve. Next, we will introduce mini loop, inner and outer loops, and the control system separately. The mini loop is designed for solving the chip-level hotspots with vapor chambers. The vapor chamber consists of a sealed vacuum vessel and an internal wick structure. The wick structure contains a small amount of fluid in equilibrium with its vapor to transfer heat from one side of the chamber to the other. When a hardware component attached below generates heat, the fluid absorbs the heat and immediately vaporizes and rises to the condenser, driven by the pressure difference. Once arriving at the condenser, the vapor condenses again and releases the latent heat of condensation to the cooling water. The condensed fluid finally returns to the evaporator. Thanks to this vapor fluid mini loop, there are many benefits of the vapor chambers. The vapor chamber can reduce the overall hardware temperature and smooth the temperature distribution as shown in the simulation figures. Also, there are other desirable properties, such as space saving and cheap. While there are many promising properties of the vapor chamber, how can we integrate it into the cold plate to take full advantage? For the copper-based cold plate without the vapor chamber, it's directly attached to the hardware component with a layer of the thermal paste. A straightforward idea for the integration of the vapor chamber might be directly inserting the vapor chamber between the hardware component and the cold plate with an additional layer of the thermal paste. However, we find this is exceedingly inefficient in transferring heat due to the much longer thermal path. Instead of attaching the vapor chamber to the bottom of the cold plate, we replace the cold plate's base plate with the vapor chamber for achieving a short thermal path. To verify the effectiveness of our approach, we conduct an experiment to compare the CPU temperature when using the through approaches. From the cooling setting of low water temperature to high water temperature, our approach keeps outperforming the others. The inner and outer loops are designed for solving the hardware-level hotspots. Instead of providing cooling water with the same temperature and flow rate for each hardware component, we design dual cooling loops that provide customized cooling water with different temperature and flow rate. This fine-grained cooling control can significantly reduce the amount of required cold water and save the cooling energy. Let's look at an example. Suppose there are 3 components in total, and their utilization levels are 100%, 50%, and 10% respectively. For the conventional cooling system with only one cooling loop, to ensure the safety of C1, maybe only the cold water is visible. In this case, 6 units of cold water are consumed, and C2 and C3 are overcooled. As for the proposed cooling system with 2 cooling loops, C1 is still provided with the cold water, while C2 can be provided with warm water, and C3 can be even provided with hot water. In this case, only 3 units of cold water are consumed, and all hardware components are well cooled, reducing the amount of cold water by about half. The control system is designed for realizing real-time cooling. There are 2 kinds of controllers. The subcontroller first collects all hardware information like power and utilization, and then send it to the centralized controller. After deciding on the best cooling setting, including the water temperature and flow rate for each hardware component, the centralized controller sends back the cooling decisions. Finally, the subcontroller sends the cooling control command to each valve for tuning its flow rate. For each heterogeneous hardware component with varied utilization levels, how can we decide on the best cooling setting in real time? As mentioned before, the energy savings of warm water cooling come from the less use of the chiller by leveraging the natural heat dissipation in pipes and tanks. When warm water flows in the pipe, the heat carried by the water can be dissipated to the outer air, since the water temperature is much higher than the air. In order to select the best cooling setting, we first quantify the natural heat dissipation P that is determined by the temperature difference between the cooling water in the pipe and the outer air, the water flow rate, the convective heat transfer coefficient of the air, and the parameters related to the physical characteristics of the pipes and water. Accordingly, we design a heat dissipation-oriented strategy. It calculates the amount of dissipated heat, converts the value to the energy that would be consumed by the chiller by multiplying the coefficient of performance of the chiller, and subtracts the energy consumed by pumps that is approximately proportional to the total water flow rate. By maximizing the final results, it can obtain the best cooling setting. Although the HDO strategy provides precise cooling settings, it could be infeasible if some parameters in the formula are inaccessible or varying dynamically. Therefore, we also develop a more practical chiller power-oriented strategy that calculates the cold water provision of all hardware components. By minimizing the total cold water provision, it can obtain the best cooling setting. Based on the cooling strategies, we devised a fine-grained cooling solution to customize the best cooling setting for each type of heterogeneous hardware components. For the computing hardware including the CPU and GPU, the hardware temperature is determined by the real-time hardware utilization, water temperature, water flow rate, and also the hardware type. Based on this observation, the cooling solution first collects all thermal profiles in advance. Then, it selects all possible settings that keep the hardware temperature below its self-operating temperature at runtime. Finally, it leverages the HDO strategy or the CPU strategy to obtain the best setting from the set to minimize cooling energy. For the memory hardware with the low power consumption, the water flow rate has little influence on the hardware temperature, as the generated heat can be timely taken away, whatever the water flow rate is. As for the water temperature, it directly influences the hardware temperature variation rate. The temperature variation rate is defined as the reciprocal of the time spent to raise or reduce the hardware temperature by 1 degree Celsius under the specific hardware utilization, current hardware temperature, water temperature, and also the hardware type. Based on this observation, the cooling solution first collects all thermal profiles in advance. Then, it selects all possible settings that keep the hardware temperature in the next period below its self-operating temperature and runtime. Finally, it obtains the best setting from the set to minimize cooling energy by maximizing the water temperature directly. To evaluate our solution, we choose real water traces from Sub-Server. The traces include the utilization of power information of CPU, GPU, and DRAM. We consider two baselines in our evaluation. For the conventional coarse groundwater cooling baseline, we set the global water temperature and flow rate according to the highest cooling demand of all the hardware components. For the state-of-the-art TC baseline, the TCs are used to deal with hotspots and consume extra energy. Since this solution is only applicable to CPU, we only use the CPU trace in the comparison. We also built a hardware prototype to verify the practicability of CoolEdge. Here are the results of the cooling energy and partial PUE. We investigate two cases in the evaluation, including the homogeneous system with only CPU and the heterogeneous system with CPU, GPU, and DRAM. As we can see, our solution can lower the cooling energy by up to 81.81% and improve the partial PUE to as low as 1.02, which means if the hardware consumes 1 unit of energy, our solution only needs another 2% of energy for cooling. Our solution is also effective in eliminating hotspots. We define the self-operating temperature of 3 hardware types according to their thermal design power. As we can see, although the maximum hardware temperature gets higher by applying our strategies as compared to the coarse-grained strategy, no hardware component runs above its self-operating temperature. In summary, our solution achieves good balance between the cooling energy reduction and hotspots elimination. We also estimate the cost savings from our solution and the TC baseline as compared to the coarse-grained baseline. The final results show that our solution can save $21.96 per server per year, which means a saving of over $3 million for 2,000 small-scale edge data centers every year in a city. In summary, our work introduces a hotspot-relievable warm water cooling system, which is energy efficient by using a fine-grained cooling control, safe by implementing a real-time cooling control to avoid hotspots, practical since it's easy to deploy and saves huge amounts of money, and tailored to edge data centers with heterogeneous and high-density requirements. Our work also intends to motivate more clean computing research from computer architects, as the carbon neutrality and carbon peak of NT systems has become a critical global issue. That's all. Thank you.